In the unit of work, energy, power, we shall be looking at the definition of work. The everyday definition of work and the one that we use in physics are quite different from each other. When most people think about work, they think of the job they have. I wake up in the morning and I go to work. In physics, however, we use two very exact definitions of work. The first definition of work is that work is a transfer of energy. When work is done on a body, it transfers energy to it. When the body does work, energy is transferred away from it. The second definition of work in physics is that work is a force acting upon an object to cause a displacement. There are three key words in this definition: force, cause, and displacement. In order for a force to qualify as having done work, it has to be the cause of a displacement. Let us consider a body at rest on a surface. It is acted upon, therefore, by the gravitational force and by the normal reaction force. Neither of these forces are doing any work because they do not cause a displacement. Now let us consider an applied force F acting on the object. Under the action of this applied force, a displacement is caused of the object through a distance that we can measure as d. Therefore, since the force was the cause of the displacement, work has been done. While the applied force caused the displacement and therefore did work, the normal force and the gravitational force were not the cause of the displacement and therefore did no work. Mathematically, the work done in this situation can be expressed by the equation work done equals force times distance times the cos of theta. Theta in this case can be expressed as the angle between the displacement caused and the direction of the force. So when the displacement is parallel to the direction of the force, as in this case here, the angle theta is 0 degrees. So that means that the cos of the angle theta, cos of 0, equals to 1. Considering the normal and the gravitational forces, the angle between the line of action of the force and the displacement moved is 90 degrees. The cos of 90 degrees is 0. That explains that no work is done by the normal or the gravitational force. If the force, however, were acting at an angle theta to the displacement, then the work done will be the force multiplied by the actual displacement caused multiplied by the cos of theta. Let us consider the same situation again, but this time concentrate on the frictional force. The applied force causes the body to move to the right in the direction of the applied force through a distance d. The angle of the frictional force, however, in relation to the displacement of the object is 180 degrees. The cos of 180 degrees is minus 1. Therefore, the amount of work done by the frictional force appears to be negative. What that means is that energy is removed from the system. It is the body that has to do work against the frictional forces. So while the applied force gives positive work to the body, and therefore the body gains energy, the frictional force removes energy from the body. We said earlier that work is a transfer of energy, and also work is a force acting upon an object to cause a displacement. Both these definitions are encompassed in this equation. Work done is equal to the change in energy caused in the body, which is equal to F times D times cos theta. When Fd cos theta is positive, energy is gained by the body. When Fd cos theta is negative, energy is lost by the body. When energy is transferred to the body, that is what we mean by the body gains energy. When energy is transferred away from the body, that's what we mean that energy is lost by the body. If the work done on the body happens to be 10 joules, then the energy transferred to the body is also 10 joules. This is known as the work-energy theorem. So the work done is equal to the energy transferred. That is the work-energy theorem. Therefore, saying that work is a transfer of energy. And also, work done is defined as force acting to cause a displacement through a distance d in the direction of the force. Work and energy are both scalar quantities, and since they're equal to each other, they have the same unit of work. The unit of measurement is the joule, both for work done and for the energy transferred.